Today, the concept is about polarization and its types. So, there are four types of polarization. They are electronic polarization, then you have ionic polarization, then the third,
Orientation, polarization, space
excellent.
state,
What about the fourth?
space charged polarization.
Excellent. So these are the four polarization. Under electronic polarization, in all these polarization, we are going to see the displacement. We are going to calculate the displacement between whom and whom. That's the matter. Okay. So displacement in electronic polarization, you will identify a displacement between electron, cloud, and the nucleus. So electron and nucleus. Displacement between these two charges. In ionic polarization, displacement between cation and anion. You will calculate the displacement between. Okay, in cation and anion, which is positive and which is negative? Which is positive and which is negative in cation?
Cation positive, anion negative.
Okay, this is positive and this is negative. The analog of cation and anion will be cathode and anode, where cathode is negative and anode are positive. Then orientation polarization, this happens in the case of polar molecules. So example, I've shown you in the introductory session about H2O. So polar molecules, they lack symmetry. That's why the negative and the positive will be separated. That is, even in the absence of external electric field, the positive and the negative will be separated. So orientation polarization takes place in the case of polar molecules, and also it depends upon the temperature. In space charge polarization, it is due to the accumulation of charges in the electrodes. Okay, so if there is a positive electrodes and a negative electrodes, so here in space charge polarization, there will be a diffusion of charges. So the charges get jumped from one place to another place. Thereby, you get a redistribution of charges. So we are going to see one by one in detail. Okay, moving to the first polarization, which is called as electronic polarization. The first polarization is called as electronic polarization. It's a derivation. So that's why I just took a whiteboard, because if I just keep on spelling out all the or reading out all the equations, that won't be that much interesting. Okay, electronic polarization. This is the first topic we are going to see here. In electronic polarization, consider an atom. Okay, inside the atom, we have the so-called nucleus, which is present in the center, and the charge of the nucleus will be plus Zt. Zt, and the charge of this, so this portion is called as the electron cloud. This is minus Zt. You know that the inside the atom nucleus is present with protons and neutrons positively charged. All the electrons will be revolving around this orbit around the nucleus. So the orbits and the electrons can be combined together and said to be an electron cloud. And the shape of this atom is considered to be sphere. Shape of the atom is considered to be a sphere. Okay, so where do these electronic polarization occurs? So they occur in monoatomic gases. Monoatomic gases, say for example argon, krypton, helium, etc. Okay, so here electronic polarization, I'll just show the steps which we are going to follow, right? So we have considered an atom. Inside the atom, we'll apply electric field. On the application of the electric field, there will be a displacement which is produced. From the displacement, we will calculate the electric dipole moment or electronic dipole moment. From the electronic dipole moment, we will calculate the polarizability. At last, electronic polarization PE. So this is the steps which we are going to do. Atom, application of the electric field, calculate the displacement, apply in electric dipole moment, then polarizability, electronic polarizability. So here the suffix E represents the electronic. That's why for ionic, it will be mu I, alpha I, and pi. At last, we will end with electronic polarization expression. Clear? Okay. So here, as I've already said, atom is being considered. So this is without the application of the electric field, without E. Okay. First of all, we have to calculate the charge density. So how much number of electrons are present in this electron cloud? So let us calculate the charge density of electron cloud. Okay. So in general, what is density? In general, what is meant by density? We'll just I'll just put let it be a rough column. Okay. In general, what is density? Density is equal to mass by volume. Here it is charge density. Charge density is charge divided by volume. So we need the electron cloud's density. Then the charge of the electron cloud is minus Zt because they are electrons. Z represents the atomic number of electrons. Okay, and E is the charge of the electron. Charge. What is the value of the charge? E is equal to 1.6 into 10 power minus 19 coulomb. So this is the charge divided by volume. So for this, we said the shape of the electron cloud, shape of the atom is in the spherical shape. So hence we have to substitute the volume of the sphere. So what is the volume of sphere? Volume of sphere is given by 4 by
4
3.
by 3 pi r cube.
Yes. And what is this R? R is the distance from the nucleus to the electron cloud. So R is the radius of the sphere. Hence we can replace here 4 by 3 pi capital R cube. So now you just put this 3 on the numerator. So 3 by 4, we have a negative sign in the front, Zt by pi R cube. Let it be equation number 1. Let it be equation number 1. So I'm just giving you the derivation, but in between sentences and all, you have to refer the learning material and you have to write. Okay, I'm just giving all the important equations how we are going to get the polarization. So the consider an atom, all those stories you have to write in between. Okay, so we have completed without the electric field. Now, on the application of the electric field, what is going to happen? So with the field, with electric field, what is going to happen? So when an electric field is applied, what happens is there will be shift in the nucleus. So on the application of the electric field along this direction, the nucleus tries to move towards the direction of the electric field. So this is my original position, but it has been displaced to a new position. Okay. So the distance between them, so displacement is x. So with respect to the displacement, I can draw another sphere. I can draw another sphere with the distance x. Okay, this is the new shifted nucleus. So let me color it. So this is the shifted nucleus and this is the old nucleus. So they are inside the atom. They are inside the atom. Okay, they are inside the atom. So with respect to the shifted nucleus and the old one, that is the original one, displacement has been produced, which is represented by x. So here there are two types of forces that is being acted. Okay, when the electric field is applied, the nucleus is moving towards the positive direction because direction of the electric field because nucleus is said to be positive. And what about the negative electron cloud? They move in a direction opposite to that of the electric field. So this electron cloud entirely shifts along this direction. Shifts along this direction. Okay. So in order to maintain them in equilibrium, there will be two forces. One force will try to pull the electron cloud or try to pull the nucleus away from the original state. That is called as Lorentz force. Or you can say like this: a force applied on the electron cloud is nothing but the Lorentz force. So it just tries to pull the electron cloud away from the electric field. And the another force is that Coulomb's force of attraction. So that is present inside the atom itself. What is Coulomb's force? Force between two point charges is directly proportional to the charges and inversely proportional to the square of the distance between them. This is called as Coulomb force. So the Coulomb force tried to maintain or come back their equilibrium position, whereas the Lorentz force tried to repel away. So there are two forces which is acting here. One is Lorentz force and the other one will be Coulomb force. So I can just put this as Lorentz force, Lorentz force, and this is Coulomb force. So under equilibrium, two forces are acting in an atom. So Lorentz force is actually a force of repulsion, whereas Coulomb force is a force of attraction, or attractive force. So in both cases, if you write the equation for force, it is nothing but charge into field. Here also, force is represented as charge into field. Charge here, the field is electric field. So here capital E, here also capital E. Here the charge is ZT. Here the charge is minus. Here also it is ZT. Okay. So the equation for electric field, that's alone, it's a different here. So here, what to substitute for this electric field? Okay, so we have ZT into the according to Coulomb for equation for electric field, it is Q divided by 4 pi epsilon naught here x square. The distance is x square. So we just put x square here. So Q divided by 4 pi epsilon naught x square. Here the charge. So actually in Coulomb force there should be two charges. One is positive or the negative, or both are same charges. So in an atom we have two charges. One is positive and the other one is negative. The positive comes from the nucleus and the negative comes from the electron cloud. So then we have to find out the charge value for the electron cloud. But we have consideration that we have found out the charge density of the electron cloud in the beginning without the application of the electric field. So with the help of this equation only, just going to substitute for Q in the place of Q. So you know that charge density is equal to charge by volume. So this is the same thing we just thought in the beginning. And what about charge? Charge is equal to charge density into volume. Charge density into volume. Here the charge density is equation 1 minus 3 by 4 Zt by pi r cube. And here, what is this volume? Volume is here the volume of this particular sphere with the radius x. The imaginary sphere, no? With respect to the displacement, I have just drawn a sphere, and for this sphere, I am going to calculate the charge. So here 4 by 3 pi x cube. I should put x cube. So this is the term I am going to substitute for q. So q is the charge. So in the place of q, I'm just going to substitute this one. So I'll be getting like this. So let me rub this a little, and I just move towards the left hand side. Okay, this ZT is already there. ZT capital E, let it be there. On the right hand side, ZT for the nucleus, and in the place of Q, let me put this 1 by 4 pi epsilon naught x square separately, and the place of Q alone, I'm just going to substitute minus 3 by 4 ZT by pi r cube into 4 by 3 pi x cube. Okay, so in this equation, let us just cancel out all the terms which are similar. Okay, so here 3 goes off, 4 goes off, pi cancels out, and we have ZT and ZT this side. What else we can just cancel? Yes, here x cube is there, so here x square. So x square goes off, here x will be there, only x will be there. Okay, so here you have the negative field because the Lorentz force of repulsion acts on the electron cloud. So that's why we have to include a negative sign. So here a negative sign will be appearing. So this negative sign also will cancel out each other. And here ZT and one of the ZT on the right hand side. So you just pick out all the terms left over will be E is equal to ZT x divided by 4 pi epsilon naught capital R cube. So 4 pi epsilon naught capital R cube. Okay, so this equation. So I can just rearrange this expression and I can get like this. So rearranging to get displacement is equal to this 4 pi epsilon naught capital R cube goes to the left hand side and joins with capital E. This ZT will comes to the denominator. I get ZT now. So this is the expression for the displacement I have just calculated. Okay, what is the next step after displacement? I have to calculate the electric dipole moment. The equation for electric dipole moment will be mu E is equal to, you know that what is electric dipole? Two equivalent opposite charges separated by a distance. So which is given by mu is equal to q times x. Okay, here the distance is x. So here also, instead of q, you have the charge to be zt into x. So substitute for x here. You have 4 pi epsilon naught capital R cube capital E divided by zt. I can just strike off zt in the numerator and zt in the denominator. So finally, I can just write like this: mu E is equal to 4 pi epsilon naught capital R cube into E. So, by looking into this expression, I just think over that there is also another expression for electric dipole moment in terms of electronic polarizability. So, that equation is nothing but mu E is equal to alpha E into capital E. So, this is an expression in terms of electronic polarizability. So, in the beginning, we have seen these equations. Okay, as the electric field is increases, the possible of creation of the dipoles also increases. Hence the proportionality, because both are directly proportional, and the proportionality can be replaced by a constant which is called as electronic polarizability. Now what shall we do? I need an expression for alpha E. What can I do now? I can just compare both expressions. Left hand side mu E, no problem. Right hand side I have E and E. So here in the place of alpha E, I have 4 pi epsilon naught capital R cube. I can just combine this. So now I'll get alpha E to be 4 pi epsilon naught capital R cube. And the unit for this polarizability is farad meter square. So the next task is also over. We have calculated the alpha E also. So what is the last one we are supposed to do? We have to calculate the electronic polarization, which is given by electronic polarization. So suffix should be E, which is equal to the number of atoms into polarizability into capital E. So if you substitute alpha E here, you get the final expression for electronic polarization. That's it. So we have done with electronic polarization. We have calculated electronic polarization. So if you check in this equation, this polarizability just depends upon this R alone. That is, if you know the radius of any monoatomic gas, you can easily calculate the electronic polarizability. Okay. So is the derivation is clear, guys? Is the derivation is clear to you? So do you want me to say once again, guys? Yeah, are you here? Naveen, you are the only person who will respond. Naveen,
Ma'am,
Naveen,
ma'am,
is the derivation is clear?
ma'am, ma'am, this is Naveen.
Yes, Naveen, tell me. I just want to know whether the derivation is clear. We have completed electronic polarization. So as there is no response, I think this the derivation is clear. Can I take this? Others in this class, Naveen, please mute your microphone. Others in the class, may I know whether the derivation is clear? Otherwise, we can proceed with the next polarization without delay.
It's
Guys,
clear, ma'am. We can go to next one.
thank you so much. Okay, next we are moving to the next type of polarization, which is called as ionic polarization. Once again, ionic polarization also has a little derivation like electronic polarization in a similar way. Okay, so the next polarization which we are going to move is ionic polarization. So, like electronic polarization, I've started a fresh page. So, the heading is ionic polarization. So, this is one of the bigger questions which appears frequently. So, ionic polarization. Here also we have to consider the displacement. Here in this case, I have already mentioned the displacement we are going to calculate between the anion and cation. Displacement between cation and anion. For this, let me take the example of NaCl. Okay, so this is Na and another atom I'm just going to consider this Cl. So here I have NaCl. Okay, so when you consider that the field is being absent or without field, without electric field, NaCl will be close together. Okay, they will be in a equilibrium state. When a field is applied, an electric field is applied, they just shift from the equilibrium position. So Na will go this side or Cl, okay. They just shifted from the equilibrium position. Na and Cl. Okay. So now you get two types of displacement, two displacements. One is x1, the other one will be x2. Okay. So when we want to calculate the total displacement, this will be the sum of the individual displacements x1 plus x2. X is equal to x1 plus x2. So like electronic, I'll just give you the steps which we are going to follow. So here we have considered cation and as well as the anion and its displacement. Then we have to calculate the x, individual x1, x2 we have to calculate. Then total displacement x has to be calculated. Then we just go for mu I, that is dipole moment due to ionic polarization. Then alpha I and finally pi. So this is the steps involved in calculating the ionic polarization. Okay, so without field, there will be an equilibrium condition. When the field is applied automatically, they just move apart. And when the field is just removed, they come back to the original state. So you get an action of spring. Okay, so there will be some restoring forces which is acting here. Because of the application of the electric field, there will be a force of repulsion that is acting on the charge. And the restoring force, so the Lorentz force will try to move apart, and the restoring force trying to bring the NaCl back to the equilibrium position. So you get a spring action in the case of cations and anions with the application of the field and remove. Okay, so this is the example which I have taken. So what is my first work? To calculate the x1 and x2. So let me put like this: anion and cation. I'm going to calculate parallelly for both. Okay, So anion and cation. So for anion, so which is anion? Cl is anion and cation is Na. Okay, cation is Na because this is positive. Cl is negative and the sodium is positive. So anions and cations. So here anion, you have to calculate the, or let me put in the reverse so that I can I'll get just a minute. So anions and cations. Okay, I'll just put cation this side. So cation, and this is anion. Here I have to calculate x1. Here I have to calculate the x2. So the two forces which are acting in the system is the one of which is the Lorentz force. The other one will be restoring force because it's tried to maintain the equilibrium. Restoring force. These are the two forces. Here also, Lorentz force. The other one will be restoring force. So in Hooke's law, you would have studied this force, restoring force. So by Lorentz force, you know, is a force acting on a charge. So E into capital E. Here also, E into capital E. So this is cation, this is anion. Okay. So now this will be equal to the restoring force. So we have to give an equation for restoring force. Okay. According to restoring force, Hooke's law, you remember this equation. Hooke's law. Stress is directly proportional to strain and force is equal to minus kx, where k is the spring constant. This k I am just going to replace by beta 1 into x1, and here it is beta 2 into x2. So instead of k, I have just put the replaced by the symbol beta 1 and beta 2. This beta 1 depends upon the mass of the cation and the natural frequency of the cation. That's all. So, so this beta 1 is the constant of proportionality or the spring constant or the Hooke's constant, which depends upon two factors. One is the mass of the cation, the other one is the square of the natural frequency of the cation at which it is vibrating. Likewise, you can write for beta 2 also. Mass of the anion and square of the angular frequency, because both will be vibrating the same natural frequency omega naught square into x2. So we have just written, so under equilibrium this is the state. So under equilibrium both cation and anion undergoes these types of forces, Lorentz force and restoring force, to maintain them in equilibrium. So, and we have framed the equations also. The next job is what? We have to write an expression for x1 here and we have to write an expression for x2. So, this x1 will be equal to, so what we should do? This m omega naught square goes to the denominator. This capital M omega naught square goes to the denominator. So, this here E divided by small m omega naught square. On this side, I get small e capital E divided by capital M omega naught square. So we have calculated the individual displacements. So first task is over. Now we have to calculate the total displacement. So this total displacement will be the sum of both. So total displacement x is equal to x1 plus x2. So let us just substitute those. So E divided by small m omega naught square plus E divided by capital M omega naught square. So let us remove all the constant terms, that is the terms which are similar. So E divided by omega naught square, I'm just putting outside in front, and let me put this capital E behind. So this E by omega naught square and capital E are the common ones. So within the bracket, I can just substitute 1 by small m plus 1 by capital M. So we have just found out the total displacement. So this is the equation for total displacement. So the next is, after finding the total displacement, we have to calculate the electric dipole moment due to ionic or ions. So next job is to find out mu I or mu ionic, which is nothing but charge into displacement. Charge into displacement. So in the place of charge, I can put E, charge of the ions, into displacement is x. So E into, in the place of x, I can just substitute this equation. E divided by omega naught square into 1 by small m plus 1 by capital M into capital E. So thus we have got an expression for electric dipole moment due to ionic as mu I is equal to E square divided E into E square. Omega naught square already available. So into 1 by M plus 1 by capital M into capital E. So we have done with ionic electric dipole moment also. Then we are supposed to calculate the alpha I. For this, I can just compare this equation with alpha I into capital, like what we have done in electronic polarization. Now let us compare. Let it be equation number 3, let it be equation number 4. So when you compare equation 3 and 4, you will get the equation for alpha I. So which is given by, so you can just write, okay. So here left hand side and right hand side almost similar except alpha I. So I can just combine the term before electric field. So mu, so I need just alpha I. So alpha I will be equal to E square divided by omega naught square into 1 by small m, mass of the cation, mass of the anion. That's all. So we have found out the ionic polarizability. So last is, we have to go with ionic polarization. The expression is number of ions into alpha I into capital E. So which is equal to n, substitute E square and omega naught square into 1 by m plus 1 by capital M into E. That's it. So this is the equation for ionic polarization. So we have done with ionic polarization now. That's all. Over. So this term indicates that this ionic polarization depends on the reduced mass. So 1 by m plus 1 by capital M, so it's referred to as reduced mass, and it is inversely proportional to the square of the natural frequency. Other things are just constants. Okay, even the reduced mass is a constant default value. Omega naught square is the vibration. It acts or it is calculated or estimated based on the electric field applied. So this is the inference from ionic polarization. So here it depends upon two factors. So this ionic polarization depends on reduced mass, so which is given by 1 by m plus 1 by capital M. So this is capital M. Okay. And number two, it depends upon the, or inversely proportional to, I can just put, because it comes in the denominator. So proportional to inversely proportional to square of the angular frequency, square of the natural frequency of the vibrating ions, natural frequency. That's all. We have done with ionic polarization also. These are the two big derivations. The rest of the things are very simple to understand. Okay. So is this ionic polarization clear to you? So I just given you in steps. What is the next, what is the next, and what is the next, how to compare, and finally what is the expression for ionic polarization. Clear?
Yes, ma'am.
Very good. Okay. So we are just moving to the fourth polarization. So I'll just share this recording of today's class so that you can just make a note on it. So the next polarization which we are moving is called as the orientation polarization, no derivation. Only one equation is there to compare. So this is orientation polarization, which is the third polarization, orientation polarization. Here it mainly deals with the polar molecules. When we saw about the difference between polar molecules and non-polar molecules, we identified some features, that is, they have or they possess electric dipole moment even in the absence of external electric field. Even in the absence of external electric field, when E is equal to 0. So this is the similar to what we have seen in paramagnetic materials. And non-polar molecules can be considered to be a diamagnetic materials because their character seems to be similar. So in paramagnetic materials, they have random spin, that is random magnetic dipole moment in the absence of the magnetic field. Here, polar molecules possess electric dipole moment in the absence of the electric field. There magnetic field, here electric field. And also these polar molecules lack symmetry. Lack symmetry. So if they are symmetrical, so it is very difficult to have a dielectric dipole moment because all the positives and negatives has to be separated. What is polarization? Separation of the charges. They lack symmetry. So I just put symmetrical. It should be symmetry. They lack symmetry. So some examples of orientation polarization are H2O, then CH3Cl, CHCl3, and etc. So the others H2N2, CCl4. Then there are several elements we can say which is non-polar or does not possess orientation polarization. Okay. Now let us calculate orientation polarization expression. So I'll just draw some diagrams for H2O. So here oxygen, this is hydrogen. Hydrogen is positive whereas oxygen is negative. Okay, so in simple way, I'll just show the random orientation. So this is negative, positive, this is negative, positive. Likewise, I can just put some random orientation. So negative, and this is positive. So I can just put in a similar way several molecules in random direction. Okay, this is in the absence of the external electric field. So in the presence of external electric field, what happens is, so all the molecules will be pointing in the same direction. I can just draw the diagrams and I can place in several ways like this. So let me move a bit, they'll be like this. So all the positives will be in one direction, all the negatives will be in another direction. So if I just place an electrode like this, okay, this is an electrode. So this is in the absence of the external electric field. So all will be oriented in random direction. So several molecules I just put over here. Okay. So the first one is In the absence of the external electric field, the second one is with the field. With field, and this is without T. They show random. They are not in random. They are all the positives will be in one direction, all the negatives will be in other direction. Okay. So since I have said that polar molecules are similar to paramagnetic materials, in paramagnetic materials, I'll just make a comparison. Paramagnetic materials and here polar polar molecules. In paramagnetic materials, we use magnetic field. Here we use electric field. There you get the process called as polarization. Sorry, magnetization. In polar molecules, you get the process of polarization which takes place. So, according to famous theory, and its derivative part is also there, but it's not in our syllabus. Langevin theory of paramagnetism. The intensity of magnetization can be written as mu square divided by 3 kT. Here mu is the magnetic dipole moment. This is in the case of paramagnetic materials. So since the features of polar are similar to paramagnetic material, I can just take this expression but replace with polarization. Here it becomes polarization is equal to electric dipole moment square divided by 3 kT. Polarization is equal to mu square. So what is this mu? Mu is O. Okay, mu is sorry. This polarization is orientation polarization, and this is O into here magnetic field will be appearing. Here electric field has to appear. So orientation polarization is equal to mu O square divided by 3 kT, and it depends upon the temperature, inversely proportional to the temperature. Okay, so when you compare this polarization expression with the polarizability, including polarizability, on comparison, you get an expression for alpha O, which is nothing but mu O square divided by 3 kT. So this is the only expression in orientation polarization, and it is inversely proportional to the temperature. Okay, K is the Boltzmann constant, mu O is the electric dipole moment due to orientation polarization. So then last what you will write the expression for orientation polarization, which is equal to N alpha O capital V, which is equal to N mu O square divided by 3 kT into capital E. So this is orientation polarization expression. Okay. And finally, we have the last polarization, which is called as space charge polarization. With that, I'll just stop for today. And we have ended with Unit 1, a small topic called as internal field. If time permits, I'll proceed. Or you can just come to the offline class, you can ask about that. So, space charge polarization is the last one. So here there is no equation, just a description, some explanation alone we just look over. So this is PS. Okay, in space charge, so the under equilibrium condition, you can observe the charges are oriented like this, whereas in when an electric field is applied, so this is in the absence of the electric field. When electric field is applied, all the charges get redistributed like this, all the negatives and positives get redistributed. Okay, when it is applied to an external electric field, this is weak field. So here the concept is called as diffusion takes place between the ions. So diffusion is also called as the jump. There will be a jumping of the ions, and they get shifted because electric field is applied along this direction. So all the positives will be moving towards the direction of the applied electric field. So this space charge polarization is directly proportional with the temperature. Hence, if you keep on increasing the temperature, the space charge polarization will also increase. Hence, this type of space charge polarization takes place in the case of semiconductors. The best example for space charge polarization is semiconductors. because as you increase the temperature in semiconductors, automatically what happens? The electrons and holes are created. Electrons starts to conduct. So the conductivity is shown in a semiconductor when a temperature is increased. That too, in the case of silicon and germanium, they are intrinsic semiconductors. So the detail of these semiconductors we will study in unit 3. Okay, that's it. We have completed with polarization. Now let us write the total polarization. P total is the sum of all the polarization, PE plus PI plus PO and PS. Since there is no equation for PS, we just neglect and write the rest of the equation for PE, PI and PO. So which is given by N, E, and just put it outside the bracket. So inside I get alpha E plus alpha I plus alpha O. So this E has gone a long outside. So I just bring and keep it here. Next, what I will do, I just substitute the equation for alpha E, alpha I, and alpha O. So don't go away. I have to share an attendance link. So be stay in the class. This is E squared by omega naught square into the reduced mass and alpha O. So we have seen just now mu o square divided by 3 kT. So capital E outside, and in the front you have the number, and this is P, that is total polarization. This equation is called as Langevin-Debye equation. This is called as Langevin-Debye equation. That's it. We have completed with the polarization concept today. Okay.